Okay, so in this topic, we're going to consider electric flux, Gauss's law, which is very powerful when you have symmetry, and we're going to look at application of Gauss's law. So we're going to do a few examples. So first of all, we just want to consider the two figures that are presented um, in this slide. And on the left-hand slide, we have a surface which encloses an electric dipole. Okay, so that means that it's got a positive and negative charge of equal magnitude. On the right hand side, we've got two charges, but this time the positive charge is twice as large as the negative charge. So what we see is when we have an electric dipole, the same number of field lines is going to be leaving through the surface as there are coming back into the surface. Okay, so we're going from the positive charge to the negative charge. Okay, so the overall net flux here is going to be equal to 0. On the other hand, on the right hand side, we're going to have a net positive flux because we're going to have more field lines leaving the surface than there are re-entering the surface at that negative charge. So what this tells us is that the flux is related to the total charge that is enclosed by some surface. Now this is a qualitative form of Gauss's law. So the flux density is the number of field lines per unit area perpendicular to the field direction. So let's consider that we have a surface, and we're going to consider that we've got some field lines which are passing through perpendicular to that surface. So here's our surface, which is going to be given by an area A. And we've got field lines which are passing through perpendicular to the surface. Now this surface is nice and smooth and flat. Okay, so this is going to be our electric field passing through perpendicular. Okay, so now we can write our flux, which is the total number of field lines passing through a particular area, as E, which is electric field perpendicular to that surface, times A. Now, let's supposing we have in fact some surface which is going to be at some angle. It's not directly perpendicular to the field lines, and here we've got the field lines passing through it again. And the surface makes some angle theta with the field lines. Well, now we can write the flux as the dot product of our electric field and our area. Okay, because remember the dot product is going to pick out that component which is perpendicular to the surface, okay, which is going to be equal to E A cos phi. Now what we consider it here is a flat surface. Supposing we don't have a flat surface. Let's suppose that we've got a surface which may be a round surface, or just a surface which is not uniform over the top of it. So what we can consider here now is that we have our surface again, and through our surface we have our field lines. Okay, so the total surface here is going to be A, and here we have our field lines again which are passing through. Okay, so this is not a smooth surface. Okay. So now what we must do is we must break our surface up into infinitesimal surface area elements. So each of these field lines will be passing through an infinitesimal surface area element A. So now we can neglect any non-uniformities that may exist on the surface. So now we can write an expression for our flux through each of these infinitesimal surface area elements as the phi, which should be equal to E dot dA, and now our total flux is just going to be the integral over the surface. So now we have phi is equal to the surface integral of E dot dA.